Hi, welcome to Social Research Insights. The mission of Social Research Insights is to promote open source software for data analysis. This is in fact one of my presentations in continuation to the previous presentation that I explained about reliability analysis through spreadsheet applications like Microsoft Excel, LibreOffice Calc, and Numeric. But in this video, I'm going to use PSPP to perform reliability analysis. As explained in my previous video, that the PSPP is used as a open source alternative to IBM SPSS, which is a proprietary software. So PSPP has all basic mechanisms to perform statistical analysis, ranging from very basic summary statistics to advanced techniques like factor analysis, cluster analysis, multivariate regression, correlation, etc. So in this video, I'm going to explain the reliability analysis through Cronbach alpha. And this is the data matrix. The window which you are looking at is actually the data view of PSPP, in which we have a data matrix of 100 cases and 10 variables. And each variable in data analysis, each column is regarded as a study variable, but in reliability analysis, the column is regarded as testlet or item, and each item will be having some certain levels. In this data, we have 5 levels. 1 stands for highly dissatisfied and 5 stands for highly satisfied. So given some certain data in this way, how do we perform reliability analysis? That is the case. Okay, we just have to go to menu analyze, and there we have a sub menu called reliability. You just have to press that, and after that we choose all the variables that need to be considered for the reliability analysis, and we go ahead. But before going to talk about the procedure of performing the reliability analysis, let me introduce you the concept of the reliability. The reliability deals with the internal consistency of the testlets or items given in a data matrix. In this case, we have 10 items ranging from x1 to x10, and we are actually interested to verify if this data is going to explain a common unique underlying factor, which is usually thought of as a general factor. In factor analysis, we use this term general factor. A general factor is actually a latent variable which is being described by the items or the testlets in the data in reliability analysis, whereas in factor analysis the definition for the general factor is different. Say here we have 10 variables, and as I said, in reliability analysis we treat them as testlets or items. We have 10 items. Each item has 1 to 5 levels. So as I said, 1 stands for highly dissatisfied and 5 stands for highly satisfied, and that is actually the method of collecting the data through measurement scale. In this case, I used Likert scale. So any researcher might be knowing about Likert scale. Likert scale is a scale which has some certain anchors, and each anchor will be having a label. So here we have 5 labels for Likert scale, and ranging from highly dissatisfied to highly satisfied. And now coming back to the concept of reliability, so given some certain number of variables like this, so the assumption of reliability analysis assumes that all these testlets or items are going to explain a common construct, which is in other words also known as, in other words I can also say that a general factor. In factor analysis we call general factor, but in reliability analysis we call common construct a unique common construct. Other words, I can also say an underlying latent variable. Okay, so this is actually the basic assumption in reliability analysis. So when we perform the reliability analysis, so we are actually testing this assumption whether the data actually explaining a common latent factor or not. So for that we have different approaches. One of the important approaches is through Cronbach alpha. So we have a wonderful measure called Cronbach alpha. Some statisticians call them as Cronbach alpha. I prefer to call it as Cronbach alpha, and we can either write as alpha or we can also write the Greek letter alpha. So whatever it may be, it doesn't matter. So you can write it as English alpha. So there are other apart from Cronbach alpha, we also have other measures. They are Revel's beta, and Gutman lambda, and David's omega. So all of them belongs to the theory of reliability analysis. So we can use any of the, but mostly researchers try to use Cronbach alpha, which is very precise, simple, and easy to calculate. And David's omega is also another simple method that which offer calculation of the reliability measure known as omega. But alpha and omega, both of them are sensitive to the outliers, and it needs the continuous data, and the data most of the time need to be numeric. So this what is this alpha, and how do we need to calculate this? So I just will explain a couple of minutes how to compute the alpha. There are different procedures to compute the alpha from the raw data and from the covariance matrix and from the correlation matrix, covariance matrix and correlation matrix. So we can use any of these matrices, correlation matrix, I just simply write it as MAT. So there are three approaches to compute. In case if we are using, if you would like to compute the alpha from the raw data, we have to use a simple formula, k by k minus 1. K stands for number of testlets, 1 minus sigma for all I, sigma square y I square. So I rather write it as xi. So instead of yi, better write it as xi because I don't like to confuse you. xi divided by sigma square y. So this is the method which we need to use to compute the alpha in the case if we need to find the alpha from the raw data, and in case if we would like to find the alpha from the covariance matrix, then we have a different formula which goes this way: k multiplied c bar by v bar or nu bar, whatever it may be, k minus 1 c bar. So this is the formula which we need to use in case if we would like to find the alpha from the covariance matrix, where the c bar is actually the average of the covariances of the upper triangular covariance matrix. So actually covariance matrix will be in this way, x10, and here we will be having something like that, and here the diagonal. So we neglect the diagonal, and here we will be having the values. So these are the covariance. Say for example, this particular value is the covariance between x1 and x2. So this is upper triangular matrix, the upper triangle part of the covariance matrix. So we just have to take the covariances from this upper triangle matrix and find the average, and that average is treated as C bar. So C bar is the average of the covariances of the upper triangle covariance matrix, and nu bar is the average of the variance of the variables. Say for x1 we'll be having sigma square x1, and for x2 we'll be having sigma square x2, and for x3 we'll be having sigma, so on and so forth. So at last we'll be having sigma square xn. So we just have to take the average of all these variances, that is V bar. So this is the method of finding alpha from the covariance matrix. And the last one is the correlation matrix. The correlation matrix is a little it has a very it is the product of the covariance matrix, and here in correlation matrix, instead of covariances we'll be having correlation coefficients. So in the same fashion we have to take the, as we compute the C bar from the covariances, we have to compute the R bar from the correlation matrix, and after computing the average average of the correlation coefficients of the upper triangle correlation matrix, we substitute that value in the same formula K R bar by, instead of nu bar we use 1 plus K minus 1 multiplied R bar. So this is the approach in case if we would like to find alpha through correlation matrix. So we just have to obtain the average of the correlation coefficients of the upper triangle of the correlation matrix, which is known as R bar, and from the R after substituting the R bar in this formula we'll get alpha value. So these are the three approaches. We can use any of these approaches to compute the Cronbach alpha. This is approach number 1, and this is approach number 2, and this is approach number 3. So these are the three approaches to compute the Cronbach alpha. So usually when we compute the Cronbach alpha through PSPP or SPSS, it uses the first approach number 1. So it computes the variance of the individual testlets or items and sum of the variances, and that sum is used as the numerator, and this is the peculiar statistic which we need to compute from the sum of the values of the test items. I mean, this is the variance of the total score obtained from the individual scores in the data matrix. For example, so here we have a data matrix of say we have x1, x2 and till x10. So here what happens, we create another variable known as y, where these n1, n2 till n10, so all these values will be summed up, and this total is taken as n total. So this is actually n final value, and in that way we compute for all instances. So I mean the cases. So we have 100 cases in our data set, so we'll be having n total 1, n total 2, n total 3, so n total 100. So for last case, so this is another variable which we create from the scores of the testlets or the values of the items, and after finding this variable we finally compute the variance of this variable, and that is known as sigma y square. So this is the value which we need to use in the denominator. Okay, so this is how SPSS or PSPP calculates the Cronbach alpha when we trigger the action. So let's go back to PSPP, go to analyze and go straight away to reliability, and you will be having a context menu in which you can see clearly that there are all the 10 variables are listed the left side window, and take them to the another sub window under the items, and by default you have alpha here. The other measure is split, which means split half alpha, split half measure. So I'm not going to deal with this the measure in this video, so you just leave that default. In case if you are interested, you can also interested in summary statistics, you can also select this option. For time being I'm not interested in this, so I just untick this and straight away go to OK and press OK. Now you'll be having the output in the output window. In case if you would like to change, this is actually not the interactive window as we do in SPSS. In case if you would like to have an editable file from the output, just export that into ODT, which means open data text format. Go to the desktop, and there you can create as I name it as rel, save, and go to the desktop. You'll be having that file. I'll try to change that in some other partition. I think my computer has some problem in saving the file on desktop. So instead of I call it as rel and go choose the option ODT, and you can also go for the other options here, but I already explained in my other video. So I'll go to F drive, and there I'll try to save that, and let me see if this time I can see. Yes, it is there. So here the file which I saved in the name rel is available from the F drive. Press OK, and now this time you after you open the file, you should be able to see that output, the same output which you look at the PSPP output viewer. The same output is also available through the LibreOffice Word file. So delete all unnecessary information from this file, and you can straight away start writing the interpretation to your outputs, so that it is easy for you to use this output in your research reports. I just try to center them so that it looks nice. Now, so look at the value Cronbach alpha. Here we have 0.09, and which is unacceptable. So this data is not in support of our assumption that we have a common underlying factor. So the internal consistency is violated rather very severely, so that this data is not useful for further analysis, which I mean factor analysis, cluster analysis, or maybe multi-dimensional scaling, anything, whatever it may be. So we cannot proceed ahead for any further analysis because the data lack the internal consistency, which means this data is not measuring any latent variable. So all of them are trying to be unique from each other. There is a criteria to assess this value. This is actually the Cronbach alpha, and there is a criteria I'm going to explain. I'll explain you how to assess this. The assessment criteria for Cronbach alpha is that if the alpha is less than 0.5, then it is unacceptable. So we are not going to accept the value. The internal consistency or the reliability is highly violated, so the data is not useful for further analysis. If the alpha value falls between 0.5 and 0.6, then it is poor. And if the alpha value falls between 0.6 to 0.7, then it is acceptable. There are different assessment criteria given by different researchers, but this is the criteria which I usually follow. And if the alpha falls between 0.7 to 0.8, then it is good. You can treat it as good. I mean, the reliability or internal consistency in the data is good. And if the alpha value falls between 0.8 to 0.9, then it is very good. Some people interpret that as excellent, but I interpret as very good. The alpha anything above 0.9 is regarded as excellent. So this is one common commonly accepted criteria or assessment criteria to interpret the alpha. Okay, so here actually it is less than 0.05, which it is not even we cannot compare that value with 0.5. So I'm sorry, it is not 0.05, it is 0.5. So the value is unacceptable. The internal consistency is severely violated, and the data doesn't possess reliability, highly unreliable, and it violates our assumption that all the variables, or our assumption, the common assumption for the reliability analysis is that the variables are trying to measure a unique underlying latent variable known as general factor. So in this case, this data is not explaining any factor. I mean, there is no factor which is unique, commonly explained by these items. Imagine that if this is the data that has stemmed up from some certain talent assessment, and these are the tests. I mean, imagine that we have conducted some 10 tests on employees, and all these tests must be having some common goal, isn't it? So I mean, every test will be having a goal, some certain objectives, and these objectives will be having a goal. So the instructor, or maybe the examiner, whoever executed this test, at last, after finishing this test, he can use the Cronbach alpha and can decide if that common goal, or the objectives of the very objectives of conducting these tests is achieved or not. So in this case, actually, since these tests are not addressing any common factor, so the very objective of conducting these tests has not been met, and they are not in fact trying to assess. I mean, these tests are not objective. So that's what we can conclude at last. Okay, thanks for watching, and please view my other videos of statistical analysis. Thank you.